In the previous lecture, we gave an example contrasting almost sure and mean square error convergence. Now we'll contrast mean square error and improbability convergence on a similar game setup, which is this time the double or quarter game. So I start after the n-1 round n-1 of the game. If my money is a n-1, I win with probability p in the nth round, and my money doubles. And with probability 1 minus p, my money reduces to a quarter of it. This is called the double or quarter game. At each round, I win with probability p and lose with probability 1 minus p independently from round to round. And this is interesting, more interesting to analyze perhaps than the double or nothing game, because in the double or nothing game, once I lose, I'm out of the game. So it is easy to see that with probability 1, my fortune will converge to 0, no matter how large it is to begin with. So we will now explore what happens in this case if I start with an amount of fortune, positive amount of fortune a sub 0. Okay, so let's first look at the evolution of my expected fortune. Clearly, the expected fortune after n rounds, it is easy to see by iteration, is 2p plus 1 minus p over 4 to the power n times a sub 0, where a sub 0 is a positive value that I started with. Okay, so this is 7p over 4p plus 1 over 4 to the n a 0. Okay, so as long as p is greater or equal to 3 over 4, in this case, the expected fortune blows up. So does this mean this is a very advantageous game to play? Would you go ahead and play this game expecting unbounded earnings? Now, perhaps we need to consider the situation in more depth. Okay, so in order to do that, let's analyze what happens to the expected squared fortune. And then let's explore what happens to the fortune, the convergence in probability. Okay, so now similarly, the expectation of an squared given an minus 1, following the similar iterated expectation argument that we used in the previous lecture, we can compute the expectation of an squared. First, let's compute the conditional expectation of an squared given an minus 1. It's p times 4 an minus 1 squared plus 1 minus p an minus 1 squared over 16. Okay. So this is 63 over 16 p plus 1 over 16 a n minus 1 squared. Right? So then expectation of a 1 squared given a 0, the starting fortune, is 63 over 16p plus 1 over 16 a 0 squared. Okay. Now, when you want to compute the expectation of a 2 squared, you can use iterated expectation. Expectation of a 2 squared given a 1 and a 0. The inside, the inner expectation is simply 63 over 16p plus 1 over 16 times a1 squared. And then I need to take the expectation of this with respect to a0. So given a0, and I iterate basically one more time and obtain this coefficient squared times a0. So what is going on is the iteration after 2 rounds is this factor squared times the initial fortune. So my fortune is increasing like this value to the nth power, and if this value is larger than 1, the square of my fortune is blowing up to infinity. Okay, so if p is larger than a certain value, and in this case, let's see, if 63 over 16p plus 1 over 16 is larger than 1, then my fortune, the expectation of my squared fortune is going to blow up to infinity, i.e. if p is larger than or equal to 15 over 63, expectation of a n squared is blowing up to infinity. So a n does not converge in the mean square sense to anything. Particularly, it does not converge to 0. Okay, that we know. Okay, for values of p larger than 15 over 63, that is. Now, similarly, if p is larger than 3 over 7, oh, there's a typo here, 3 over 7, if p is larger than 3 over 7, expectation of an also blows up. So I said, do you think this is a advantageous game to play? Now let's explore improbability convergence. I claim that an actually converges in probability to 0. This would be an example of a case. Remember, I drew this sort of set relationship in the previous lecture. This would be an example that falls somewhere here, where there is improbability convergence, but there is no mean square error convergence. Let's see that. Let's explore the limit as n goes to infinity of the probability an minus 0 being bigger than some positive value epsilon. Well, now in order for this, the fortune to stay above a certain number, essentially we need a sequence with more winnings than losses. Okay, so this is equal to the limit as n goes to infinity of a binomial sum from 2n over 3 to n, and choose k, p to the k, 1 minus p to the n minus k. Now, I will show that this is true for a specific value of p, because for every value of p, you can explore this separately. In this case, it is enough to show one value of p where improbability convergence exists while mean square convergence does not. And I am going to pick p equals 1/2. Okay, so setting p equals 1/2, this is the limit as n goes to infinity of 1/2 to the n summation n choose k. Now, you know already that summation n choose k, if I sum from k going from 1 to n, I get 2 to the n. Okay, that would mean the sum is constant. However, I'm not summing from 1, I'm summing from 2n over 3 to n. And that creates all the difference. This means this sum is less than 2 to the n. It rises slower than 2 to the n, increases more slowly than 2 to the n. So this limit is 0. This shows that in probability convergence exists. So your fortune actually will converge to 0 in probability. That is, if the game is fair, meaning if p is a half, while your expected fortune and your expected squared fortune blow up to infinity. This example actually also shows us that expectation can be misleading.